Alright, so welcome back to the OneClass channel. Again, my name is Joey. I'm going to be your chemistry teacher for this session. So here at OneClass, what we're aiming to do is, because despite the school closures because of COVID-19, we've been basically very lucky to allocate all our resources, and being an online education kind of resource in the first place, we've been we've been kind of pivoting very well as to kind of this in this atmosphere. What we're doing here in this session is that we're verifying kind of commonly asked questions or frequently asked questions in both chemistry as well as mathematics. So we've been very fortunate to kind of compile and have a resource of all these questions. And what we're doing here at OneClass Teachers is that we're going to verify these solutions for you as well. So that you're able to have the best resources going into a future course, or if you're taking a course right now, hopefully you'll find these resources valuable. So my name is Joey. I'm currently a chemistry teacher. I'm a secondary school educator in Ontario, and my teachable subjects are chemistry, and I'm hoping to get a mathematics teachable very shortly. So let's get started on today's problems. We have 10 problems for today, and again, these problems are kind of ranging from mostly grade 11 to kind of university level chemistry. All right, so it says it's asking us which of the following should have the highest boiling point. So this is question 1. So let's do question 1 here. So question 1 is asking which of I want the highest boiling point or the highest BP, and don't want that, highest BP. And A here is I have CF4, B here would be CCl4, C here is CBr4, D here is CI4, and E here is CH4. We're asking which of these guys have the highest BP. So let's look at a periodic table, because we're going to need to know our periodic table for this guy to solve this problem here. And what we have here is we have all of these guys are bonded to carbon, right? So as you can see, A through E here, all of these guys are bonded to carbon. And the only difference is we have some halogens here. We have fluorine 4, chlorine 4, bromine 4, iodine 4, and we have CH4 here. And again, this is methane here. And CH4 isn't actually a halogen. H4 is not a halogen in this case, but A through E are halogens. So it's asking us which of these ones have the highest boiling point. So there's kind of some factors to figure out boiling point. And the first one is, the biggest one here is in the intermolecular forces. So the intermolecular forces of these compounds determine the boiling point here. And basically, the greater the forces, it would equal the higher the boiling point. And remember, there's a lot of intermolecular forces. There's hydrogen bonding, there's the London dispersion, there's dipole, and a lot of these things here. So let me just draw a sample of the first one guy here. This is CF4. So we have carbon here. We bond to this fluorine here, fluorine here, fluorine here, and fluorine here. And as you can see here, there's actually a dipole moment, right, between this carbon and fluorine. You see this bond here. We have a partial positive on this carbon here, and the fluorine is actually pulling electronegativity towards this fluorine, right? So this pulling this way, this way, this way, and this way. And what that means is if it's pulling all 4 directions here, we actually have a net dipole for this molecule is 0, right? Because again, these two vectors would cancel out, the left and right would cancel, and the top and bottom would cancel out. So these dipole moments would cancel out, and these dipole moments would cancel out. So therefore, there's actually no dipole in this moment, and this compound is actually nonpolar, and it's actually nonpolar. So this actually happens with all of these guys here, A through E. These are all nonpolar molecules, and CH4 we already know it's nonpolar because carbon and hydrogen, again, they don't have a big electronegativity difference, so we already know it's nonpolar here. So all of these guys are therefore nonpolar. So if we can't find this out in terms of intermolecular forces, we need to be able to solve for it using atomic size. So basically, Let me erase these guys here. So we know we figure that all of these compounds are nonpolar despite having different halogens. But the other factor that plays into part is the London dispersion forces, right? So that was for dipole-dipole. We know that there's no hydrogen bonding, right? In this case as well. So the only force that's left here is the London dispersion forces. And with all London dispersion forces, again, the greater the molecular weight, the MW, the greater the force is. Which means the greater the force is, obviously, the higher the BP, right? So we're basically now picking which of these guys have the greatest molecular weight. So all these guys have carbon, so we can kind of cancel these guys out first. Sorry. All of these guys have carbon, so we can cancel them first. But what we can do is we can look at the second part of the compound here. So we have F4 here. We have chlorine 4, bromine 4, iodine 4, and H4, right? So obviously H4 has the smallest molecular weight because, again, hydrogen here is 1.008. 4 of them, it's 4, so it's fine. And then basically I'm looking at these halogens. I have F, Cl, Br, and I, right? So F, Cl, Br, and I, which of them have the biggest molecular weight? Well, obviously iodine does, right? At 126.90. So therefore, the highest BP here in this case would be D, right? Ci4, or carbon tetraiodide would be the molecule with the highest boiling point because it has the greatest amount of London dispersion forces in the compound here. So the solution here is correct. Again, Ci4 is good. Molecular size, so larger molecule, the larger the boiling point, which is correct. Intermolecular forces also play a part, which is good. It says here all the molecules listed above are nonpolar, which is good. So all of them have van der Waals forces, or you can think of it as London dispersion forces. So therefore, however, van der Waals forces are stronger for larger molecules, right? Which is good. So that's Ci4. So the solution here is correct. Good analysis. All right, let's look at number 2. It's asking us decide whether these proposed Lewis structures are reasonable or not. So I have, this is number 2. So I have H bond O. So that's number 1. And then number 2 would be Cl bond C bond O bond Cl. 1, 2, 3, 4. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Then we have C triple bond O, like so. Okay, so saying decide whether or not these are reasonable. So we look at the first one here, and we're asking, is this proposed Lewis structure reasonable? And in this case, no, right? And why is it no here? Well, look at hydrogen here. Focus on hydrogen. Hydrogen has a maximum of can only make 1 bond. And as you can see, hydrogen here is making 2 bonds here. So there's actually a positive charge on this hydrogen here, which is not stated above, which means that this Lewis structure is not reasonable. So I can say not reasonable. Oh, maybe let me do this in red, actually. Because hydrogen is making 2 bonds. So not reasonable. And it says, no, it has the wrong number of valence electrons. No, it has the right number of valence electrons, but doesn't satisfy the octet rule. So again, this hydrogen does not satisfy the octet rule, right? Again, I'm only allowed, I'm allowed 1 bond on this hydrogen and not 2, right? There's valence electrons here. I have technically 4 valence electrons here, right? Which makes no sense. So it has the wrong number of valence electrons. So this is, so it basically says, so therefore, wrong valence electrons. Wrong, or let me say wrong valence E minus. And we can say the symbols here, if the correct symbol here is actually H2O, right? And we know that oxygen, the most negative molecule, is going to go in the middle, right? And then it's going to be bonded to 1 H here and 1 H here, and it's actually bent. The structure is actually bent. So let me, it actually looks something like this because the lone pairs are onto this side here, and this one is the correct molecule here, and this is H2O, right? As we all know. So this is not correct. So we can say this: no, it has the wrong number of valence electrons on hydrogen. So that's good. That's number 1. Let me draw a line here. Number 2 is asking us, okay, what about this compound here? Well, if we look at this compound here, we have chlorine making one bond, which is good. Chlorine making one bond, which is good. Oxygen here is only making one bond, and this is not good, right? Because oxygen here and carbon here is only missing one bond, right? A carbon likes to have 4 bonds. So in this case here, I have a negative charge on this oxygen and a positive on the carbon, right? So this is actually not good. So what I want to do instead is actually to fix this. So this, again, this is not reasonable as a structure, not reasonable. Because I have a lone pair on this carbon here that's not being accounted for, and this lone pair can actually bond with one of these other share electrons with one of these oxygens, right? So I can say that this here is this here again. I have the so it's not reasonable. You can say it does not. Again, it has the wrong number of valence electrons, right? In this case here, I have. Actually, no, it has the correct number of valence electrons, but doesn't follow the octet rule, actually. So it does not follow the octet rule in this case. Does not follow octet rule. Because again, I have these 2 valence electrons here. And the correct structure for this guy here would be, I have Cl here, bond C here, bond Cl. And this would be a double bond bonded O here. And this here would be, I have 2 lone pairs on this side. 1, 2, 3, 4, 5, 6, so 1, 2, 3, 4, 5, 6. And this would be the correct structure. Because again, carbon now has 4 bonds, which is great, and oxygen has 2. So this is the correct structure here for this compound. So again, this here is also incorrect. And finally, the last one here, I have carbon triple bonded to an oxygen here. And this guy here would be, it would satisfy actually this this compound here. And the reason why is that I have, again, carbon could make 4 bonds here, but instead it's only making 3. So I'm missing 1 here, which is fine, but it's indicated by this lone pair here. And then oxygen here, I can make a maximum of 2, but again, it's making 3, which is fine, because it is sharing these electrons with this carbon, right? So you can say that this sharing, I'm sharing these electrons here. So it's sharing, so you can say, therefore, this is good, so yes, and it's sharing 6 electrons. So the 6 electrons on carbon and the 6 electrons on oxygen are sharing. So therefore, I have lone pairs here, which actually they actually cancel as a dipole. So this here is actually a linear molecule here. So this is good, and this is simply just carbon monoxide, right? So this is a proposed structure, which is good. And again, the solution does not tell us anything here. So I'm gonna write here my solution. So solution, again, it's very, I don't know why the formatting is off here. So solution is incomplete. So I'm gonna say here for the first molecule, 1 H, not reasonable, because hydrogen cannot make more than 1 bond, 1 single bond. It contains the wrong number of valence electrons. Should have maximum of 2, but has 4 in the middle H. Therefore, the correct structure is H bond O bond H, which is H2O. Water. 2. This is also not reasonable because the lone pair on carbon should share electrons with the lone, with one of the pairs of one of the lone pairs, I'll say one of the lone pairs on oxygen to make a double bond C double bond O instead of C bond O. It contains the wrong, it does not, I'll just say it does not follow the octet rule right now. Follow the octet rule because I have a lone pair by itself waiting to, or I can say because I have a positively charged carbon with a negatively charged oxygen. Therefore, the correct structure is Cl bond C bond Cl, and or Cl bond, the correct structure is, well, or I should just say would contain a C double bond O instead of a C bond O here. And 3 here is, it's reasonable, and so it's yes because it's sharing, carbon is sharing 6 electrons with oxygen, therefore making a triple bond. This is the correct structure for CO, which is carbon monoxide. So this solution is incorrect because, again, I don't see any solution here, but I'm going to write my own solution as well. Okay, that was number 2. Let's look at number 3. Oh, sorry. It says when calcium carbonate is added to hydrochloric acid, calcium chloride, carbon dioxide, and water are produced. How many grams of calcium chloride will be produced when 26 grams of calcium carbonate are combined with 12 grams of hydrochloric acid? Which reactant is in excess, and which grams of this reactant will remain after the reaction is complete? So classic stoichiometric question here. So this is number 3. So let's say we have CaCO3 calcium carbonate plus hydrochloric acid will yield, I have calcium chloride here plus water and plus CO2. Okay, so we have all these guys here, and it's asking us how many grams of calcium chloride will be produced here. So I want to look for the mass of this guy here when I have 26 grams of calcium carbonate. So this is the mass. Calcium carbonate is 26 grams, are combined with 12 grams of hydrochloric acid. And again, I want X here, right? This here is going to be my unknown here. So I want to find the mass of calcium chloride. Or sorry, grams of calcium chloride, yes. So I have a mass here. What I want to find here is I want to find which of these guys are the limiting reagent. And then that will determine how much mass we're going to make here. So I have mass here, which means I'm going to have to find the moles of calcium carbonate and hydrochloric acid here. So I'm going to do the molar mass here. So molar mass of calcium carbonate is going to equal, so let me write this down. It's going to be, let's see, Ca here is 40, I believe. 40.078. So I have 1 calcium. So it's going to be 40 I'm going to see if I can fit this all in a chart here. 40.078 plus, I have 1 carbon here, which is 12.011 for the molar mass here. So 12.011 plus, I have 3 oxygens here, so 3 times 15.999 will give me my molar mass here. So 3 times 15.999. This is going to equal my molar mass in grams per mole. So this is 40.078 plus 12.011 plus 3 times 15.999. This is going to be a value of 100.086. And this here will be my molar mass of this compound. So 100.086. 100.086 grams per mole. So this here is my molar mass of this. And what about my molar mass of my hydrochloric acid? So let me draw a line here. Kind of not good, actually. Let me draw it like this way here. And let me rewrite this guy. 100.068 would be here. 100. Oh. 0.68 grams per mole. Again, I have 12 grams of hydrochloric acid. I want to find the molar mass of hydrochloric acid, obviously. So hydrogen, I have 1 hydrogen here, so it's going to be 1.01008. So 1.008 is my molar mass of hydrogen, and then I have my molar mass of chlorine as well, which is 35.45. It's going to be 35.45, which is going to equal, I add both of these numbers up, 1.08008 plus 35.45 will give me a value of 36.458 grams per mole. So this here is my molar mass of calcium carbonate and my hydrochloric acid. And what I can do now is I can find my moles, right? So this here was my molar mass. Let me write this in blue here. I want to find the moles now of these two guys here. So the moles is simply going to equal my mass divided by molar mass, right? So N here equals mass divided by molar mass. And this is going to equal, again, mass of, so calcium carbonate at 26 grams divided by 100.068, right? So 26 grams is the mass of calcium carbonate, and we divide that by the molar mass of calcium carbonate, which is 100.068. I'm going to get a value of 0.2598. So 0.2598, and this here is going to be moles. And then for this guy here, and what am I going to get for this guy here? So I have 12 grams divided by 36.458, which is going to be the molar mass of hydrochloric acid. So 12 divided by 36.458. And I'm going to get a value of 0.3291. 0.3291 moles. And then what I have to do now is I'm going to have to compare the mole, the coefficients first before I compare the mole values. So as you can see, I have calcium carbonate here, but then I have two hydrochloric acids here, right? So what I'm going to have to do is I'm going to have to actually divide this number by 2 because I have a coefficient of 2 here. So this here, this mole, I would have to divide it by 2 to get what is 1:1 for the mole ratio here. And as you can see, they did the mole ratio as well, right? So what they're doing here is that they are going to divide this this value by 2 here. So let's see. So they got, let's see if they got this solution correct. 0.26 and 0.3. I got 3291 here, but I think their molar mass is off by quite a bit. It's 36.5. I wrote 36.458 here, so they're actually slightly off here, which is, oh, they wrote 13 and not 12. This is 12 grams. Okay, so that's why their numbers are off here. But it's okay. We can still work with this here. What we can do is, again, we're dividing this number by 2, right? So this is the mole-to-mole ratio here. So you can think of this as I can either divide this by 2 or I can multiply calcium carbonate by 2 here. To figure out that. So if I want to do that, I would actually, in this case, what they're doing, they're multiplying this by 2, which is fine, or I can divide this by 2. So in this case, I can just follow their strategy here and multiply this by 2 here. So we get 2n here, which is going to equal, and we already know that this here equals 2n, right? So this is already, because the coefficient is already 2 here, so I can simply have to write 0.2598 multiplied by 2, which is going to be 0.520 moles. And all I'm going to do now is I'm going to compare these two values together, right? As you can see, this is 0.520, this is 0.3291, which means this here is going to be my limiting reagent. Therefore, limiting reagent, and this guy here is going to be my excess reagent here. So the question is, which reactant is essence, is excess, sorry, it's going to be my calcium carbonate here. And which one would be limiting? This would be the limiting reagent as well. So knowing this, what I can do now is I can solve for this calcium chloride, right? If this is here is my limiting reagent, I can solve for my calcium chloride. So what I have here is what they're doing here is the moles of calcium chloride equals the moles of calcium chloride divided by hydrochloric acid here, the mole ratio here. So if calcium chloride divided by hydrochloric acid, it's going to equal 3291 here, which is good. And then what I can do, and then they didn't actually finish this problem here, which is kind of concerning. But this here, I'm going to have to multiply. I'm going to have to basically multiply this by half. And that's why I wanted to multiply this by half. So let me redo this. I don't really like what they did here because it doesn't actually help us go into our solution here. So we know that this here is excess and this here is limiting. However, if I want to multiply this guy by half, because to get per mole of my hydrochloric acid here. So I'm going to divide this number by 2. It's still going to be a limiting reagent. I just like how I simply like dividing by 2 to get everything in terms of 1 mole here. This is going to be 0.164 or 165 if I were to round it, moles. And again, this is still my limiting reagent, right? Limiting reagent. So you get these guys. This is excess and this is limiting here. So that's fine. And then what I can do now is I also know my multimole ratio, right? So I know that this here is also going to be 0.165, right? This calcium chloride is also going to be 0.165 moles. So all I'm going to have to do is work backwards to figure out my mass, right? So I have to figure out the molar mass of calcium chloride. So that's very, very easy. What I can do is I already know the molar mass of calcium, which is 40.078. Plus, I'm going to have 2 chlorines, right? So I have 2 times, and then chlorine here, I said that was 35.45 here. So this is going to equal the molar mass of calcium chloride, which is 40.078 plus 2 times 35.45. So that's going to give me a value of 110.9978 grams per mole. And finally, I can solve for my x value, right? And this x value is simply, if I were to rearrange this equation, so if I know that moles equals mass over molar mass, then mass here has to be moles times my molar mass here. So I'm 0.165 multiplied by 110.978 here. So using this, so the mass of CaCl2 is going to equal the moles of CaCl2 divided by the mole, or multiplied by the molar mass, sorry. Moles of CaCl2 multiplied by the molar mass of CaCl2 here. And this is going to equal, I'll just finish it off here, I guess. Moles is, again, 0.165, like so, and the molar mass is 110.978 grams per mole here. And this is going to equal my answer. So this times 0.165 is going to equal 18.31. And this here is going to be my answer for this problem. So I have 18.31 grams. And if I were to care about the significant digits here, I'm looking at my significant digits. I have 12.0, so I have 3 significant digits. So therefore, the answer should have been 18.3 grams of CaCl2. And this here is the correct answer for this solution. And they actually did not complete this answer, so that's fine. So this solution is incomplete. Incomplete. So they got this right, which is good. So they did this part right. Or actually, no. They actually divide by 13 instead of 12 here. So let me copy and paste this. And this here should have been statement should have been 12 grams HCl, not 13 grams of HCl. So therefore, this would have been 0.3291 here. Which would equal 0.165 moles of CaCl2. And then what we can say when we know the mass of CaCl2 is going to equal moles of CaCl2 multiplied by the molar mass of CaCl2. I'll just finish off this problem for them. I'm going to say that the moles here is going to be 0.165 moles multiplied by 110.978 grams per mole. This is going to equal 18.3 grams of CaCl2. Therefore, let's see, it says here we are producing 18.3 grams in terms of CaCl2 in the reaction, and CaCO3 is the excess reagent. So solution is incorrect because they failed to complete the question here. Okay, that was question, oh, we're only question 3 here, wow. So these questions are quite long here. So it says determine whether each process is exothermic and endothermic here. Okay. So we're going to have to open up this file. So this is question 4 here. Question 4. Okay. So it says here, determine whether or not it's exo or endothermic. So I have A here, which is dry ice evaporating. B here is a sparkler burning. C here is reaction that occurs when chemical cold pack is used. So chemical cold pack is used to ice athletic injuries. Okay, so we have these guys here, and again, the solution is here, so that's good. So we care about whether it's exothermic or endothermic, and what's the definition of those two guys here? Well, as exothermic, I know that heat here is being released, and that can be in the form of multiple things. It could be actually thermal energy, sound. It could be in light, and it could be other specific. In this case, it's actually heat, so in terms of thermal energy here. And then this guy here is heat is being absorbed, right? Endothermic. So by these definitions, what we can do that, and I think it says indicate the sign here. It's just sign of delta H. So in this case here, we have dry ice evaporating. If we have dry ice here, if it's evaporating into the air, what it's doing, it is the energy, instead of, we don't have to put energy actually into the system for it to evaporate. It actually evaporates by itself here. So then in this case here, it's actually going to be a endothermic reaction because heat is actually being absorbed. It's taking energy from the air, and it's actually using that energy from the surroundings, and it's going to go through this physical change of evaporation. So in this case, this guy here is endo. And in this case, delta H here would be a positive value here. Would be a positive. This is my shorthand for it's the plus sign, and VE is positive. A sparkler burning, if it's a sparkler burning here, this is an exothermic reaction. Again, it's something is combusting. These are all exothermic reactions. Again, you can feel the heat when a sparkler is burning, right? If you kind of stick your hand close to the sparkler or close to a fire, you know that this here is exothermic. And delta H here is negative for an exothermic reaction because heat is being released into the surroundings. And finally, chemical cold pack here, this is an endothermic reaction. And why is it endo? Well, the chemical cold pack is cold, right? So it's actually taking energy from the surroundings, and it's absorbing all the energy from the surroundings, and then it's going to appear cold. So when you touch it, it feels cold. It doesn't feel hot, right? So in this case, this is an endothermic reaction. And this will have, again, delta H has to be a positive sign here. So again, the solution is correct because I believe they have this as well. So dry ice evaporating is endothermic, so that's good. The dry ice gains heat to get evaporated, therefore it's endothermic. Sparkler is exothermic, which is good, and endothermic for ice pack. So the solution is correct. That's good. Let's look at number 5. It's asking which statement about hydrogen bonding is true. Okay. So I want true statements. So A here is hydrogen. I'm going to say H bonding instead of hydrogen. H bonding is the intermolecular attractive force between two hydrogen atoms in solution. Is intermolecular force between two H atoms in solution. And right off the bat, we know that this is here is false, right? H bonding is not between two hydrogen atoms. If you recall hydrogen bonding here, H bonding only exists with three molecules, with N, O, and F here. So this here is not true. So A here is not true. B says that the hydrogen bonding capabilities of water molecules cause C3H2, CH2, CH2, CH3 to be more soluble in water than CH3OH here. So that is also not true. And I'm not going to write that down because CH3OH here is a polar molecule because there is and it also contains hydrogen bonding, right? I can say here is H bond between the H and the O here. Whereas if I had, this is CH3, CH2, CH2, CH3, this here has no hydrogen bonding that exists here. No H bonding. And this guy here is also nonpolar. And because we know that water is water, let me do this in blue because water, I know is a polar solvent. And if I know that like dissolves like, so methanol would dissolve in solution. And so this is soluble. And this guy here, butane, is non-soluble, right? Because it's nonpolar. Non-soluble. So therefore B is false because CH3 is not more soluble in water than C3AOH. So this here is not true. So I can X this B, not correct. And A here is also not correct here. I'm looking for the true statements here. C is asking hydrogen bonding of solvent molecules with a solute will not affect the solubility of the solute. Let me say that again. So H bonding of solvent molecules with a solute will not affect the solubility of the solute. Well, it does, right? Because I told you, like in this previous question, methanol here is the solute, and the solvent is water, right? So water, H bonding is in water, obviously, with a solute. This hydrogen, the hydrogens on water can also hydrogen bond with the methanol here. So it does affect the solubility of the solute because this makes it a soluble molecule. So this here, C would have to be, this here is, it would affect the solubility. So H bonding of solvent with solute affects solubility. And the reason why, so again, this statement is also false. And the reason why is that if I were to draw out the molecules here, of H here, this here is hydrogen bonding, but also have CH3OH, right? So let me write this here. So I have C3OH here. And this, so again, these guys here, so I can hydrogen bond. So this here is a hydrogen bond. Let me do this in blue. Hydrogen bond here. Again, these guys here, this is a partial negative charge. This here is a partial positive here. So again, these guys here are going to be attracted, right? This hydrogen here is going to be attracted to these water molecules, and these hydrogens are going to be attracted to this oxygen molecule, right? So this is the hydrogen bonding that exists between the solvent and the solute. So C has to be a false statement here. I have D here is asking us hydrogen bonding interactions between the molecules are stronger than covalent bonds. Hydrogen bonding interactions between molecules are stronger than the covalent bonds within the molecule. So this statement here is, so they said here is not true. But I'm thinking of the wording here. Hydrogen bonding interactions between molecules are stronger than the covalent bonds within the molecule. So so this is a trick question. So hydrogen bonding between molecules are stronger than the covalent bonds within the molecule. So again, this is not true as well. So this solution is correct, but the trick here is that hydrogen bonding, we know that hydrogen bonding is actually stronger than covalent bonds, but this has to be only within the molecule. When we talk about between the molecules, then it gets a little bit trickier. So that's kind of a trick question in the sense that hydrogen bonding is actually stronger than covalent bonds only if they're both within the molecule. But in this case, it's asking is hydrogen bonding between molecules here. This is the trick here, between molecules. So I'm going to say here, this here is also false because H bonding within molecules are stronger. Than covalent bonds. Okay, which makes the E has to be true, right? Because I had 4 false statements. It says here, hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. So this is like, so this is true, but it's actually like so, it's not as specific as I want it to be, because what we're talking about here is hydrogen bonding arises from the dipole moment created by the unequal sharing of electrons within certain covalent bonds within a molecule. This can actually be with anything, right? Then if I had a C bond F here, this here also has a dipole moment created by unequal sharing of electrons. But again, I don't have hydrogen here, so this can't be hydrogen bonding, right? This here is partial positive. This guy here is partial negative. So this question is actually not the greatest question in my opinion, because this here, if they're defining hydrogen bonding that arises from the dipole moment created by unequal sharing, then this here would be considered a hydrogen bond, right? By this definition. However, it's not, because there's no hydrogen here. Hydrogen bonding only exists with nitrogen, oxygen, and fluorine. So this is actually it's not a good question at all, actually. This here is not a good question. So I'm going to say that this here, E here is true, but in a specific condition. And I understand the concept that's happening here because they're using hydrogen and oxygen here, but I can use a counter example of this carbon bonding to fluorine, and this by definition would still be hydrogen bonding technically, which is false. So I'm going to say solution is correct, but question is terribly phrased. So I'm going to copy and paste this and say the definition, or I'll say this definition of hydrogen bonding is not true. Not true. And I give a counter example here. If I have C bond F here, in the single bond between carbon and fluorine, there is a dipole moment that creates by whatever. I'm just copy and paste this. Dipole moment created by the unequal sharing. Therefore, by definition, this would be considered a hydrogen bond. However, we know that that is not possible. It's not possible because hydrogen bonding only exists with a hydrogen. So exists with the inclusion of a hydrogen with either nitrogen, oxygen, or fluorine. So question is poorly phrased, but correct solution. So again, this is not the greatest solution here at all. D here is a bit tricky in terms of the wording. I think a lot of people would have fallen for this trap and writing D is true. But I think if they even just switched this word into within molecules here, this would have actually been a true statement, because hydrogen bonding is stronger than covalent bonding. Hydrogen bonding is stronger than dipole moments, but dipole moments in intermolecular forces. But again, it's not stronger than covalent bonds. So it's very, 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 very tricky here, this question. So the solution is correct, but I didn't really think, the phrasing of the question is just not very, very good. That's question 5. I would never ask that on a test. That's not fair to my students, because again, the wording is just so poorly phrased, doesn't get the point across, and whatever. Okay, so it's asking how many electrons and protons and neutrons are in an atom of Ca43. Okay, so at 43, Ca is asking how many electrons, protons, and neutrons. Electrons, protons, and neutrons. So every time we look at this guy here is an isotope. So let me read this down. So this here is the isotope of Ca, or of calcium here. And this 43 represents my atomic mass. Recall that isotopes are simply just the same element, they have the same protons here, but a different amount of neutrons, which affect the atomic mass. So if I look at calcium here, this here is, the atomic number is 20, which means the protons here is 20 still. So I'm going to have 20 protons. Sorry, I have 20 protons here, which is good. And I don't have a charge here, which means I'm going to have 20 electrons as well, right? So this is 20 electrons, but the neutrons are, how do I calculate the number of neutrons? Well, I have to use this formula, right? I have to say the number of neutrons is going to equal the atomic mass minus the number of protons. So the atomic mass here is 43. I'm going to subtract that by the number of protons, which is simply just 20. This will equal 23. So this here is my solution. 20, 20, and 23 is my solution. So let's look at the solution here. Calcium atomic number is 20, so it has 20 protons, which is good. If there's no charge here, it will also have 20 electrons, so they cancel out, which is good. And finally, we can say that there are how many neutrons here? Neutrons, 4 stable isotopes, which is good. I don't think they actually said number of neutrons here. So let me say solution is incomplete here. Number of neutrons is going to equal the atomic mass minus the number of protons. So this is going to be 43. Sorry, that's 53. 43 minus 20, which would equal 23. So we say therefore there are 20 electrons, 20 protons, and 23 neutrons in a sample of Ca43. So the solution is incorrect because they didn't actually give me I had an incomplete solution here, so that's okay. Okay, let's look at number 7. I don't know how many more I can finish within the next couple of minutes, but we'll see if we do 2 more here. Number 7, click on the carbon atom that should be designated as number 1 when naming the compound systematically. So I'm going to draw this out here. Let me draw it out straight here. So I have a pentagon bonded to some CH3 here. It's going to bond to CH2, CH3. Let's bond to CH3. And it says which of these 5 carbons will I choose first? So it's either this one, this one, this one, this one, or this one, right? Well, in this case, I'm looking at the parent chain here is simply the this is a cyclopentane chain, right? So I have 5 of them here, which is actually, this here is false, right? So this is not a cyclobutane, it's actually a cyclopentane here. I have 5 carbons. And it says here, the carbon atom that should be designated as number 1 when naming the compound systematically. Well, I have to simply just look at my functional groups, right? Or my alkyl chains. This here is a methyl group. This here is also a methyl group. and this here is an ethyl group. So which one takes priority? Well, the ethyl one takes priority, right? So this one should be number 1. If I were to continue naming this, this would be, I would go this way instead of this way, right? I want to minimize the number. So I want to go number 2. This here would be 3, 4, and 5 here. So if we were to name this, this is actually 1 ethyl, and then 2,4-dimethyl cyclopentane. And that's how you would name this compound here. So this solution is actually the wrong solution for this compound here. So solution is incorrect, is not for the right solution, not for the right question. So I can say that the carbon atom that should be designated as number 1 should be the carbon attached to the ethyl group. That's it. And then I want to I want to also name this guy, right? So I said that the naming here is, so I can say 1 ethyl. This would be, I have 2,4-dimethyl, so 2,4, and then I have 2 methyl groups, so 2,4-dimethyl, and then this here is a cyclopentane. So this here is my naming for this kind of compound here. So again, 1 ethyl here, 2,4-dimethyl, and then cyclopentane is my parent chain here. The naming for this compound is 1 ethyl, 2,4-dimethyl, cyclopentane. This solution is not correct because they actually gave me the incorrect solution for the problem here. Okay, so I don't think I have enough time for this question, unfortunately. So we're going to wrap it up here at number 7. I'll continue with this problem in terms of next week's stream when we're talking about chemistry again. But again, thank you so much for watching this stream. Again, my name is Joey. You can catch me streaming Monday to Friday. Monday, Wednesdays, and Fridays are going to be math streams. Chemistry is from Tuesdays and Thursdays, so you can check me out then. Again, thank you so much for watching. Again, you can always find these videos. They're posted now, I think, about 11 to 12 hours right after the live stream, so you can stick around for those videos as well at youtube.com/OneClass, so you can check them out there. As always, thank you so much for watching. Stay safe, stay healthy, and have a great day. Take care.